Hi, good day. I hope all of you are keeping safe. Welcome to another lecture of AEW 125 Business Statistics. In the last lecture on Chapter 6, Dr. Tay talked about how to compute probabilities from normal distribution, how to use the normal distribution to solve business problems, how to use the normal probability to determine whether a set of data is approximately normally distributed. Most of this discussion were particularly dealing with population with no sampling involved. In this chapter, we will be looking at sampling distributions, which involve the sample mean and sample proportions. Sampling distributions enable us to use a statistic, such as the sample mean and sample proportion, to estimate population parameters like mean and proportion, which will be discussed in the inferential sections in the future. In this chapter, what you will be learning is the concept of sampling distribution, how to calculate probabilities related to sample mean and the sample proportion, and also the importance of the central limit theorem. So what are sampling distributions? A sampling distribution is a distribution of all the possible values of a sample statistic for a given sample size selected from a population. The sampling distribution of the mean is the distribution of all possible sample means calculated from all possible samples of a given size. For example, suppose you sample 50 students from your college regarding their mean grade point averages. If you obtain many different samples of size 50, you would compute a different mean for each sample. We are interested in the distribution of all potential mean of the grade point averages. Thus, we might calculate for samples of 50 students. How do we develop a sampling distribution? Assume there is a population, and this population has a sample size has a size of n equals to 4. The variable of interest is x, which is the age, this part here, okay, and the values are also given, which are 18, 20, 22, and 24. So from this population, we want to do a sampling. First, what we will do is we will calculate the mean value for the population. So the mean value is denoted by this formula, mu equals to sigma xi, summation of xi's divided by n, which is your 4. So the xi's are given here, 18, 20, 22, and 24. So when you total them up, divided by your n, which is 4, you will get a mean value of 21. Next, the standard deviation, which is given by this formula, summation of xi's minus the mu which is 21, square them, and then you divide it by n. Finally, you take the square root of this value, you get the standard deviation, which is given here, 2.236. Next, we will look at how do we develop a sampling distribution. Now consider all possible samples of size n equals to 2. The possible sample that we can generate for n equals to 2 is given by this formula, n to the power of n. So your population is 4 and the sample size is 2. So 4 to the power of 2, you get 16 samples. So how do we generate the 16 samples? We will look at this table. So the first observation and the second observation. So the first observation here can be 18, second observation 18, first observation 18, second observation 20, first observation 18, second observation 22, and so on. Once we calculate these numbers, we have 4 here, 8, 12, and 16. So we have 16 possible samples that we have generated with replacement. So once we generate these samples, for each sample, we will calculate a mean value. So 18 and 18, 18 plus 18 is 36. 36 divided by 2, you get 18. 18 plus 20 is 38. 38 divided by 2, you have 19. So when you calculate all these mean values, so we will get some mean values which are higher than your population mean. Some mean values will be lower than the population mean. What we will do next is to generate a distribution from all these mean values. So we see here 18 appears only one time, 19 mean value of 19 appears two times, mean value of 20 appears three times, a mean of 21 appears four times, and here 22 three times, 23 two times, and 24 appears only once. So we will draw them in this plot here with the probability of appearance and also the mean values. So what we will get is, now you see the distribution is normal compared to the distribution that we got earlier, which was a uniform distribution. We will now calculate the mean value for the sample, which is denoted by mu x bar. So the sample 1 had 18, sample 2 19, and so on until the last sample had a mean value of 24. Divided by 16, we will get a value of 21. So if you find here the 21, mean value of the sample is the same as the mean value we got from the population. Okay. The second formula we have here is called the standard error. Okay, the standard error is actually mu x bar here equals to each of the xi's minus the mu, square it, and then when we total up, we will now divide by 16, not 4, because now we have taken 16 samples. So the standard error that we get will be 1.58. Now this is the comparison between your population distribution and sample means distribution. So the population has the n equals to 4, and our sample means distribution has an n equals to 2. The distribution in your population was actually a uniform distribution because the probabilities were the same. 18 one time, 20 one time, 22 one time, and 24 once. The mean value was 21. The standard deviation was 2.236. Whereas here, for the sample, for the means distribution, we have 16 samples. 18 appeared once, 19 appeared twice, 20 appeared three times, 21 appeared four times, and 22 three times, 23 two times, and 24 one time. So the mean value for the sample is 21. The standard error equals to 1.58, which is slightly lower than your standard deviation, which is given in your population. Since your mu x bar is equals to mu, x bar is actually an unbiased estimator of your mu. Different samples of the same size from the same population will yield different sample means. So a measure of the variability in the mean from sample to sample is given by the standard error of the mean. The standard error of the mean, which is here, sigma x bar equals to sigma divided by a square root of n. Since we divided by the square root of n, so the note here is standard error of the mean will decrease as the sample size increases. That is one of the reasons why in many studies they always suggest to take a bigger sample size. Thus, the conclusion is, if a population is normal with a mean of mu and a standard deviation of sigma, the sampling distribution, which is x bar, and the standard error of the sampling distribution, which is denoted by sigma x bar, will also be normally distributed. Next, we will look at how do we calculate the Z value for the sampling distribution of X bar. So the formula for Z is given as X bar minus mu X bar divided by the standard error, which is sigma X bar. So we already showed that the mu X bar is actually equals to mu. So here we can simplify the formula to show X bar minus mu divided by standard deviation divided by square root of n. The X bar denotes the sample mean, mu denotes the population mean, sigma denotes the population standard deviation, and n denotes the sample size. What we have shown thus far is your mu X bar, which is sample mean, is equals to your population mean. In a standard normal distribution from the population, when we take a sampling distribution, the mean value for the population and the sample size will be the same. The only difference will be the dispersion in your population will be a bit larger, and the dispersion in the sample will be slightly smaller due to the fact that we will take the standard deviation divided by the square root of n. So that is why we refer to X bar as the unbiased estimate of the population mean. The sampling distribution properties are shown in this slide. The distribution, if you see here, when the sample size becomes larger, the standard error becomes smaller. When the sample size is smaller, the standard errors are actually larger. So we will now move to looking at how do we determine an interval to include a fixed proportion of the sample means. Let's say we find a symmetrical distributed interval around mu that will include 95% of the sample means when mu equals to 368, standard deviation equals to 15, and n equals to 25. Since the interval contains 95% of the sample means, 5% of the sample mean will be outside the interval. Since the interval is symmetric, 2.5% will be above the upper limit and 2.5% will be below the lower limit. So we see here that this part here, which is 95%. So we have 5% which is divided into two tails. The first part is 0.025 and the second tail will be 0.025. The discussion of the standard normal distribution, we will use this table which was given to you as an appendix Lampiran D or appendix D. So this is a distribution where the probability values given inside the table is from the mean to the Z value that is calculated. So if you want the value which is outside here, this part here, we will take this half is 0.5 minus this part, we will get the balance. How do we refer to the table? This is an example. Let's say we were looking at 5% two-tail, which is given by the Z score just now. 2.5% is in the lower tail, 2.5% is in the upper tail. So the value given here is actually from 0 to Z. Okay. So if you take 50%, 0.5, which is half, minus 0.0250, so the balance will be 0.475. So how do you look for the 0.475? The values given inside the table is what we call as the probability values. So 0.475 is actually here, correct? So what is the corresponding value for the Z corresponding value for 5% two-tail is 1.9 and 6. So that is how you look at the number for Z value. This is another example of how the probability values and the Z values correspond. So here we have an example with 5% two-tail. So we already calculated this. 50% minus 0.025 get 0.475. So in the table, we will look at 0.475 and the value corresponding value is 1.96. This is a truncated table from the table we showed just now. So the Z value for a two-tailed test is the left-hand side will be a negative 1.96 and the right-hand side will be a positive 1.96. Sometimes in the question that's given to you, you'll be asked to calculate one side of the distribution, which is called one-tail test. So if you are given an alpha of 0.05, what will happen here is we are looking at this part here, one side only. So the tail is actually 0.05. The balance, this part here will be 0.45. 0.5 minus 0.05, you get a 0.45. So the probability here is 0.45. So from the table, we don't have an actual value of 0.45. It's actually in between 0.4495 and 0.554505. So when we take the average of these two values, we'll get a 1.64 and 5. So the 1.645 is actually the Z value when your alpha is 5% and is one-sided, greater than.